Okay.
Okay, I will share my screen. And we will get started. So, great. So I hope people can see the screen. And great.
Yes, we can see it.
Great. So, okay, so I'm very, very happy to be sharing some of the things my group has been doing with you. This is in the context of accelerating enhanced sampling methods. And I will be talking about a class of methods called information bottleneck. And more specifically, I will be talking about the state predictive information bottleneck method. With this, we are looking at a diverse range of applications. So the reason why you should be interested in methods like this is so you can study problems such as nucleation of polymorphs or ligand dissociation and a variety of problems. So, and today's work is primarily done by my first PhD student, Yehang, who is now moving to University of Chicago for a postdoc, and Dedi Wang. So I have a Wang degeneracy problem. Sometimes their papers get miscited together. And so Yehang started with the original method, and Dedi has really pioneered it. And Shams has also worked a lot on it. And Shams I have to thank him for creating the tutorials that the codes on Google Colab that I will be sharing with you today. So let me start my stopwatch so I know I'm on track. So, and these are the organizations that currently support our research. So I will start from a very, very big picture and then really get into the math and show you how things are. But let's start from why all of this do we care about? So one of these books that I used to love when I was in high school is Feynman Lectures on Physics, and I still enjoy reading it a lot. It's quite a nice book to read. And one of the things Feynman says in that book is almost a trivial statement that everything that living things can do can be understood in terms of jigglings and wigglings of atoms. And in the next paragraph, he says something slightly more controversial, which is like, if you knew the lineup of a protein, you could not say what protein is to be made or what RNA is to be made. So he's almost challenging in 1963 that the protein folding problem and the RNA folding problem, in a sense, is going to be too hard to solve. So it's been a lot of years since 1963. So where are we now? So in terms of molecular dynamics, it's clear that we are really doing big systems now. I mean, this is beautiful work from Rami Amaro and collaborators where we are simulating the spike protein and, it's billion atom MD. And recently I saw, I think, 500 billion atom molecular dynamics. I don't even know how many zeros that is, maybe 10 to the power 10 or 10 to the power 11 zeros number of atoms. So, I mean, in the size problem, clearly we can keep doing bigger and bigger systems, but I think we have reached a high level of maturity that we are doing that. And last year was also a breakthrough in terms of AlphaFold and predicting structure of proteins, where it was featured on the cover of Nature. And then one morning I woke up and Forbes magazine had this news article saying AlphaFold is the most important achievement in AI ever. So if you look at this slide, it looks like, wow, we really, really have made enormous progress. Maybe we have really solved the problem. But the question is, are we there yet? So in molecular dynamics, we continue to be timescale limited. And as you have, if you have attended any of the master classes or tutorials, you know that there is a sampling limitation. And if you're attending today, you're probably aware of the sampling limitation where MD is trapped in one basin for some time. And this trapping timescale is really limited by the integration time step, which in classical MD is femtosecond. And with supercomputers or GPUs or Wall Street money, you can maybe get up to millisecond. But in order to solve a large number of problems, such as protein conformational change, crystal nucleation, or ligand unbinding, the timescales are very, very slow. And this is with classical molecular dynamics. If you start thinking about polarizable force field, if you want to use a code such as amoeba, for example, the timescale problem is even harder. And I really think maybe a few decades from now, we will all be doing more quantum dynamics one way or the other, and then this timescale problem will persist. So the timescale problem is there to stay, irrespective of whatever advances we have in our supercomputers, because as supercomputers improve, our description of reality will also improve correspondingly. And so the timescale problem is there. And we have lots of tricks, of course, to solve it. Metadynamics is one such method where you start biasing the landscape. The issue with metadynamics and basically all enhanced sampling methods, I would like to claim, is that so every month, every week almost, there is a new enhanced sampling method. When we first read the paper, the claim will be made that, oh, we don't need a reaction coordinate. We can get away with a reaction coordinate. We don't need to have it. Metadynamics needs a reaction coordinate, so it's a very bad method. We don't need it. You read more carefully, you will realize, but we do need a progress coordinate. When you start using the method, when the method starts reaching a certain level of maturity, as happened with metadynamics, you realize that while the method is guaranteed to converge without a good reaction coordinate, it helps to have a sense of this low degree of freedom. It really speeds up your sampling. And this is true for any method. Metadynamics, in a sense, is more forgiving because it's self-diagnostic. It tells you whether you're trapped in one basin or not, if you're willing to do the analysis. In methods such as umbrella sampling, you can also analyze whether you're trapped or not, or whether the sampling to be trusted or not, but it's not as direct in order to do that. It's more complicated. And I would like to argue that all of these methods, one way or the other, have that same limitation. So to summarize at this point, in multidynamics, we have made a lot of progress in solving the timescale problem, and we have also actually made a lot of progress in figuring out the reaction coordinate, which I will be telling you today. And it's not just my group, many other groups have also worked on this problem. A related problem that I will not be talking about today, maybe this will be the topic of one of the future master classes, is that even though we put so much faith in AlphaFold, it does not really have a notion of thermodynamics. And in fact, in this context, the co-organizer of this master class, Max Bonomi, wrote a very, very nice review where he pointed out that by hacking this MSA thing in the AlphaFold, you can generate different conformations. So you can maybe get a sense of conformation 1 and conformation 2, but it's very hard to rank what are the relative probabilities of the conformation. And turns out that even for simple proteins, once you start making point mutations, the relative probability changes. And while the ground state for these two mutations is the same, if you make a third mutation, the ground state completely flips. And you can try this through collab fold. It's quite easy. You will see that the arrangement of the phenyl ring, which really distinguishes these conformations, is completely missed by AlphaFold. It gets it all wrong. So, and this is something that my group is actually working on using this same method, state predictive information bottleneck that I'm talking about today. And you can keep an eye out for a preprint, I think, in maybe 2 weeks from now. But today, I will tell you more basic stuff and then really get into the tutorials of how it all works. And just one more big picture slide as to why machine learning and why do we want to do machine learning? Not just because everyone talks about it or because it's cool, but I think there is a really deep connection between machine learning and statistical mechanics. So there is this book chapter, and maybe some of you have seen it in previous presentations that I have given, where it's titled Confronting the Partition Function. So if you look at this chapter, my question for you is whether this chapter comes from deep learning book by Yoshua Bengio or Mark Tuckerman's book on StatMech. So I want to see, what do you think? So can you type in chat whether you think this chapter comes from DL? Type DL if you think comes from deep learning, type SM if you think it comes from Mark Tuckerman's book. Give me a moment to drink my coffee. You can just type in the chat. If you don't type, the tutorial is over. Okay, we have one. Okay, good. So we are talking about sampling. So at this point, we can conclude that it's primarily DL, but there are some people at least who think it's SM. So the answer is DL. And you have to take my word that when I give this in different audiences, the proportion of people, also depending on whether you have seen it before or not, that say whether it's DL or SM really oscillates between 5% to 95%. And there is a giveaway hint, clear hint that first of all, it's talking about partition function in chapter 18, right? A book on StatMech won't talk about partition function in chapter 18, but it is confusing. It even talks about Jarzynski and things like that. And so the motivation here is that both fields of deep learning and StatMech, one way or the other, have the same daemon, which is the partition function. If you can calculate the partition function, you can calculate all sorts of thermodynamic averages out of this partition function. Not kinetics, that's a harder problem, but you can calculate thermodynamic averages. And a big field of work in statistical mechanics over the last, even before Feynman, since 1950s, has been on how to avoid calculating the partition function, how to get away by calculating ratios of the partition function. And when you go and read the literature on machine learning, you will find that people have similar methods. They don't just call it free energy perturbation, they will call it variational inference. And it's the same idea on how to manipulate partition functions so that it becomes tractable. So a big part of my group is inspired by exploring such connections for the benefit of both communities, machine learning and StatMech. And Giovanni has posted the link to the Slack channel that you should fill up today before 6 p.m. Europe time so that you can get added to the Slack, which will be important for the second class also. So, and for this, my group has developed a range of methods. Today, I will be talking only about this first class of methods, which is information bottleneck. We also have this denoising diffusion probabilistic model, which actually, first we thought it just enhances replica exchange, but now we realize that it actually goes far beyond. You can, yeah, that's another discussion, and I would love to give a class on that maybe next year. And then there is a third class of methods which involves us to take a trajectory coming from experiments or simulations and then extend it very, very long into the future, even accounting for errors that you might have had in the trajectory. So you can go and play with these two methods also on our GitHub, but today we will focus on this information bottleneck. So what is this information bottleneck? So why do we need it? So let's take a very simple system. This is a 6-state system in 2D. This is coming from a nice review paper by Gerhard Stock, where you have 6 states, 1, 2, 3, 4, 5, 6. And that's it. There is no other coordinate. Now you take this 2D picture and you project it into 1D. When you project it into 1D along R1, you get 6 different states, right? 1, 4, 2, 5, 3, 6. So from the perspective of clustering, you have indeed created 6 nicely separated clusters. But this projection is totally wrong. Why is it totally wrong? Because from state 4, it shows you that you can go to state 1 or you can go to state 2. This connection is completely wrong. It's not there in the 2D picture. So even in such a simple 2-dimensional picture, if you just project and all you are looking for is nicely separated clusters, you might be completely misled. So it's easy to say that, oh yeah, this is obvious. Of course, we can see what is going on here. But then my question for you to think is, if in such a simple projection, we like to criticize it that it's wrong, or we are willing to criticize it that it's wrong, why are we willing to put so much faith into projections coming from machine learning? This is a nice review article by Gareth Tribello and collaborators from Frontiers, where they show a range of methods such as PCA, distance matching, Laplacian eigenmap. All of these, one way or the other, produce nicely separated clusters. My message to you is that not all of these are suitable for biasing in any sampling method. Some of them might be, some of them might not be. Just because you are projecting out different clusters, for the simple reason over here, if you start biasing it, unless and until the kinetic distance is preserved, you will still get hysteresis. So you have to be careful in using dimensionality reduction methods for driving your enhanced sampling. So one of the methods that is lacking here is autoencoder, which really exploded on the landscape. Basically, around the time I started my groups of Andy Ferguson and Frank Noe were really the other parallel groups who were working at the same time. And autoencoder does the same thing. In a latent space, it produces such a map. And we think, well, we have a map. Why not just bias it? We have nice clusters. So always remember this, just because you have clusters, that doesn't really guarantee anything. So we took a slightly deeper look into the autoencoder and tried to connect it with a formulation for the reaction coordinate that the community more or less agrees upon is the perfect reaction coordinate. This is known as the committer. So if you have a 2-state system and you go to various points in configuration space, not in phase space, and let's say we go to this point over here and we launch lots and lots of trajectories from here. We shoot lots and lots of trajectories and we count what percentage of them committed to state A. And so from here, it's going to be maybe 80% probability of going back to A. But from here, it's going to be maybe 20% probability of going back to A, right? Because it's closer to B. So we join all points with the same probability of going back to A, and we get this surface. So we will get these sets of surfaces, and per construction, they are going to be non-intersecting because at the same point, you cannot have 2 different probabilities, right? So originally, the paper goes back to Ansager. If you go and read his paper, he doesn't really talk about committer, but people still say that's the paper. But really, Van den Eyden, and even before Van den Eyden, Vijay Pandey in the late 90s started popularizing the committer as being the perfect projection. If you know this, you can bias everything because this tells you what state are you. It predicts this. It is a low-dimensional projection that tells you what is the state that you are going to get into certain before you go to the other state. So the problem though is the committer is hard to calculate. There are lots and lots of methods for it, but this is a 2-state picture, but reality is not really 2-state. And most of biological problems, the harder problem is that we don't even know where the states are or how many states are there. And it's easy to get caught in beautiful math and not realize that most practical problems will not be amenable to such beautiful math, because we will have to address some other issues first, which is where are the states and how many states are there, right? So my group, I actually have a mathematician in my group, Luke Evans, and I collaborate with mathematicians, and we have very accurate methods of also getting the committer using something called Mahalanobis kernel, and which is always a good way to benchmark our methods. But today I will be talking about something approximate, which is this information bottleneck. So the concept of information bottleneck, it really goes back to a very pioneering paper done by Shannon, the most famous Shannon of information theory, in early 50s. The paper is called Rate Distortion Theory. It's a great paper, you can read it, but the form I'm showing you today was popularized by Bill Bialek, I think in the early to mid 90s, and in the concept of an information bottleneck. And so information bottleneck, the idea is quite simple. Let's say you have a high dimensional data. Okay, what is this data set? This data set could be the temperature of all cities across the world today. Okay, so it's a 20,000 dimensional data set. Or it could be the temperature of all cities, not just today, but also yesterday and the day before and the day before. So it's a time series. So it's some complicated data set, very high dimensional. And you want to make some prediction on its basis. On its basis, let's say you want to predict the temperature of all cities in the world tomorrow. So you have a high dimensional input. Using this, you want to come up with a high dimensional output. Or maybe you don't want a high dimensional output. Maybe you just want to make a single prediction whether it is going to rain in Trieste tomorrow or not. That's a binary prediction, 0 or 1. So very high dimensional input, and you want to learn a model that allows you to make some high dimensional or low dimensional prediction slightly into the future. So the information bottleneck idea does on its own does not have the concept of a past future, but I'm going to stick with the past future here. So in our case, this tends to be the molecular, this is the trajectory of a molecular dynamics system. Not for all coordinates. We avoid all coordinates because then we have to worry about trivial symmetries. We look at trajectories of coordinates of order parameters that already account for these symmetries, such as contact maps or dihedrals or sines and cosines of dihedrals and things like that. On this basis, we want to predict what is going to be the value of these order parameters slightly into the future, and we will see exactly what are these order parameters and how far into the future we are looking, and you will play with it yourself in the tutorials. So this is a generic model. What Bialek says, a good model should have two properties. First of all, it should be as predictive as possible. If you're not doing a good job of predicting what you wanted to predict, then the model is crap, right? It's like homeopathy. What's the point? It has no predictive power. At the same time, the model should be as compressive as possible. If the model is not compressive, it means you are just committing everything to memory. And you are basically recapturing noise, and it tends to not perform very good on types of data that you have not seen before. So you reach this bottleneck structure where you have like two funnels, where the first funnel you are compressing as much as possible. The second funnel you are predicting as much as possible. And indeed, this is similar to an autoencoder. In fact, for training this to learn this low dimensional variable, which we call the bottleneck, we can write down a difference of two mutual informations. The first mutual information minimizes the first one is the mutual information between the input and the bottleneck. You want this one to be as low as possible. The second one maximizes the mutual information between the bottleneck and the output. Now, if the input is the same as the output, and you set this control parameter equal to 1, then you recover a variational autoencoder. So this is a generalization of a variational autoencoder. The most accurate name for it is actually a deep variational information bottleneck, deep variational past future information bottleneck. So, and in order to optimize this, and in principle, if you could optimize this problem, then given your MD trajectory from a training set, I will show you that why this bottleneck is the reaction coordinate. And in order to show that, and by the way, so we have to learn two maps now. We have to learn a map that takes us from the input to the bottleneck, and a map that takes us from the bottleneck to the output. And both of these maps are expressed using neural networks. We call this as the decoder. The decoder is almost always a deep neural network. The encoder, and we will talk about it, especially in the second class, is why it's beneficial to have a linear encoder. It helps with interpretability, but more importantly, if you're interested in really rare event problems and your starting data is coming from a bias simulation, if you use a deep neural network encoder, it appears that you end up capturing too much noise. So it's best to start with a linear encoder and switch to a neural network encoder only if you're very confident in the quality of sampling. So, so why is this a committer? So for this, we have to go one step further and think about this bottleneck variable itself. So another difference we have from a variational autoencoder, that in a variational autoencoder or in any method, you have to assume a prior for this bottleneck. So normally what is done is to assume one Gaussian prior. That's it. Why do we assume a Gaussian prior? It actually makes the math for this minimization very, very easy. Gaussians are very easy to manipulate, right? If you differentiate a Gaussian, you can integrate it, you can do all sorts of wonderful things. So here we say something different. We say that our system is not a one-state system. We are going to have multiple number of states. So why just assume a single Gaussian? Let's assume a mixture of Gaussians. So instead of being white noise, we have structured noise. We don't know how many Gaussians do we need. We don't know where are these Gaussians going to be located. So we start with a large number of Gaussians, which are located somewhere randomly in this high-dimensional space, and we let the method learn on the fly how many of these Gaussians actually preserve their population. So this work, which we published in a paper in JCP in 2021, it's basically using this idea of this paper called Vamp Prior, also by Max Welling. This has no connection with VampNet, by the way. And you adjust the labels of the state, and so this is the key idea. So essentially what we are doing now, and you really have to read this paper, the State Predictive Information Bottleneck, to see more of the math. But let's look at it through example, and this will show us. And this example is also covered in this tutorial. So you will be generating all of this completely yourself by running codes in GROMACS. So we have alanine dipeptide, our favorite molecule. We input order parameters to this method, State Predictive Information Bottleneck. As a short form, we call it SPIB. So when we put this trajectory along phi, theta, psi, omega, and you could take their sines and cosines, so it's like an 8-dimensional trajectory or a 4-dimensional trajectory, we know that the system really has 2 states or 3 states, depending on whether you want to believe, whether you care for this barrier or not, right? But a priori, let's say we don't know how many states are there. So what we do is to discretize the system along phi into 10 states, okay? You could also discretize along psi, by the way. It does not matter. And this is something you can try in the tutorial yourself. If you discretize along theta, then it won't work. But if you discretize along phi or psi, it will work quite nicely. So now you discretize this. So your Gaussian, your mixture of Gaussian has 10 states, and you try to predict the future 0.5 picoseconds into the future. When you run the method, you will see that out of the 10 states, the population of 7 of them disappears, and only 3 states are left with population. And you are automatically discovering that when you project in the phi and psi. So now, right now, I'm projecting the value of the latent variable in the phi psi space. In this case, you get 3 states automatically. Now, if you try to predict 2 picoseconds into the future, you get only 2 states, which means that this barrier disappears. So unlike methods like Markov state model, where the lag time is something you have to make it slower and slower and slower until you become Markovian. In this method, the beauty is that the lag time is a control parameter. It is a fast mode filter. Depending on what lag time you use, you will get a different resolution of the system. For enhanced sampling, we would try to take a lag time which is on the slower side, right? Because we don't care about increasing this barrier. And it is still I think it's an open question for us, and maybe some of you can give me ideas, is how to really rigorously select a lag time for enhanced sampling. Mostly we tend to be on the slower side and just stick with it. So now you can hopefully get some intuition into why this might be related to the committer. This latent variable is the least you need to know about saying which state are you going to get into the future. In fact, if you do a committer analysis along this latent variable, you get a sharply peaked committer, as sharp as you're going to get. These committers are hard to get. It's easy to show pictures where they are very, very sharp, but once you start doing it in practical systems, you need, and so it gets a sharply peaked committer. And if you see in this paper, this intuitive idea is made a bit more mathematical. that if we go back to this committer picture, it is this projection. The latent variable characterizes essentially the surface from which we know which state are we going to go into next. And it's really, I mean, the math is almost trivial as to why this is the committer, because the probabilistic framework is really inherently built into all of this. So that's alanine dipeptide. Let's go to slightly more complicated system, which is sodium chloride ion pair dissociation. So far, I haven't told you about sampling with this. I'm just trying to give you motivation as to why this past future bottleneck is related to the committer. For a two-state system, the value of the latent variable tells you exactly where you are going to commit next, right? For a three-state system, it's more general than committer, and you can get things like this. So if you go to sodium chloride, this is a classic system people use to study reaction coordinates. Here, you want to think about what's a reaction coordinate. So the most naive component of the reaction coordinate would be the distance between the two ions, right? But turns out for this system, waters also have to move. So along with the R ion, you can also think about number of bridging waters between the two atoms, the waters which are shared by both of them. Very easy to calculate in PLUMED by using joint coordination number. So here we start with a 10-state description of the system, and we try to predict 8 picoseconds into the future. We get only a two-state system. 8 of the 10 states, their population disappears, and essentially you have an associated system and a dissociated system. But as you keep decreasing the time you are predicting into the future, you start to see these configurations in the middle where the ions are separated by the same distance, but you have different metastable states corresponding to the number of water molecules in between. And you can do a full transition state. Ignore this Gaussian truncated model. That's to show the effect of long range versus short range. But look at this one. So you can do a full committer analysis and calculate the distribution of transition states. And you can do this directly from our method coming from one long unbiased trajectory, or you can use other excellent methods such as likelihood maximization and calculate the same thing. And you again get the same distribution of transition states from both methods. So with these two examples, and by hopefully giving you the motivation that you are really talking about the state to which you are going to commit, this past future information bottleneck is the reaction coordinate or an approximation to the true reaction coordinate. And I want to show one more model system, then show you some more complicated applications. This is a nice entropic two-state system popularized by Ron Elber, but also many others. So here you have a bottleneck in which you have to go from state A to state B. So the question is, how would the transition state look for this one? So this is work again done by my grad student Shams and my postdoc Eric Baerle. The paper is out for review at JCTC. So here you can calculate the committer surfaces. So I'm directly showing you the committer now using the latent variable. So for the latent variable, I just have to plot the value of the latent variable, and that's it. I don't need to do any more committer calculation. From Markov state model, there are ways of solving the Chapman-Kolgo-Morov equation or whatever and get the committer. So you can see they are very indistinguishable if you do from Markov state model. Here, I want to show something what happens with TICA. If you do TICA, since it's a linear method, you completely miss out that the reaction coordinate gets clumped in the bottleneck. And and for sampling, so this is something which I found quite interesting, that we need non-linearity in our description of the bottleneck as soon as entropic thing starts to dominate. If it's really an energetic thing, maybe you don't need it that much, but this is just what currently in the review. So let me show you the full picture now. So the full picture is that now we have some unbiased trajectory or some biased trajectory generated using some biased sampling method, metadynamics, method ensemble, whatever. You take this trajectory, you have to account for weights of the samples, and you take this trajectory and learn a past future information bottleneck. I really recommend using linear encoder when you start out, unless you are really confident that you're close to the truth. A deep linear encoder will try to capture too much of the noise. And when you do metadynamics along a deep linear encoder, many times you will find that your sampling actually goes down. It becomes slower. And that shows you that you have just captured too much garbage. So you take this past future information bottleneck, as I tried to motivate, it is close to the reaction coordinate. You use it to do your enhanced sampling. Mostly we do metadynamics. We also have work on method ensemble. I will show you very briefly. It's not published yet. And then we iterate, we get a superior trajectory where the system is doing more back and forth. In ligand unbinding, there is really no back and forth, it's just out, but it's with lower weights that it goes out. And you keep iterating, don't publish at this point. Take this, learn a new reaction coordinate, and hopefully do 2 or 3 rounds until you show that the reaction coordinate has converged and the sampling is not further improving. So yeah, and then this is just a teaser for weighted ensemble, and the code for this should be out maybe in a couple of months. That's another story, where this is capped LR3, and we are trying to do weighted ensemble to discover all possible states together, not just starting state and ending state. And here we are doing weighted ensemble as we are learning the state predictive information bottleneck on the fly. And you can see we can get kinetics, because you have 8 states here. So 8 choose 2 is 8 multiplied by 7 by 2. So that's 28 transitions. And you can get very good kinetics for almost all 28 of the transitions compared to long. Well, actually for all of them. In long and biased MD, you never really So this is something which should be out in a few months and ready to use in PLUMED. So let me show you some more examples for SPIB, then I will take some questions and move to the tutorial. So this one is out on PLUMED Nest, and the files are mentioned at the end of the second tutorial. You can go and try it for yourself. It's a synthetic peptide, AIB9, again from Gerhard Stock and Peter Ham, which can exist as a left-handed helix or a right-handed helix in explicit water. So if you do, so here we are learning a reaction coordinate as a linear combinations of the sine and cosine of the phi and psi of all 9 dihedrals. So 9 multiplied by 2 is 18, their sine and cosine 36. So we have 36 coordinates, and we are actually learning a nonlinear encoder as a combination of these 36 coordinates, which is improved through metadynamics until the system does back and forth. Similar thing for GB1, and this is for ligand permeation, where we can get benzoic acid to permeate through this bilipid layer, go to the other side and come back. Not everything is sped up here because part of the problem is entropic, and that is something where maybe we should use adaptive Gaussian metadynamics to speed it up, but the energetic parts we can speed up. And we have, this paper is now out in Angawante Chemi, where we look at kinases. And this was actually not using, I'm clumping 2 classes of methods, which is using information bottleneck, but also using my previous method, Scoop. In this case, this was Scoop, but it is a similar idea where we can get the kinetics for these 2 systems in good agreement with experiment, explain why is one sequence having a slower kinetics, one sequence having a faster kinetics, but more than that, we can get really kinetics across orders of magnitude in agreement with experiments or D-short trajectories with these class of methods. And this one is accepted in ACS Central Science. It should be out soon, where this is actually RAVE. So we don't do state prediction, we do prediction of the coordinates of the system. And here we could get the system to, for different mutants, for different ligands to dissociate, and we could make predictions for which mutations matter more for different ligands. On this basis, ideally we should have predicted, the experimentalists should have checked the kinetics, but as a crude approximation, they just tested the KD and they found our predictions, different types of prediction, to be quite accurate. So I'm not going into details of the application because the papers are out there, but I'm just trying to show you, give you a flavor for the type of things you can do with it. And we can also look at polymorph nucleation. We should have these 2 papers should be out soon, where we are nucleating urea in solvent in water and glycine also in water. We are getting different polymorphs. And these are really hard problems. We don't just want the crystal to form. We want to go back to the liquid, go back to another polymorph, and really get hysteresis-free movement in the, if you look at the time series, going between different polymorphs. And we are able to do that also using state predictive information bottleneck. So, and in this case, of course, the order parameters have to be a bit more boutique. You don't have contact maps, so we have to consider these curated order parameters, such as the entropy order parameter from Pablo and Michele and others. And it turns out entropy actually plays a huge role in the reaction coordinate. So let's see. So with that, I think I'm ready to conclude this presentation and then walk you through the first tutorial. We have a range of methods. You can check them on GitHub, and I really advise that you open github.com/tiwari-lab right now. That's where I'm going to screen share and show you some of the things. So maybe I take 5 minutes of questions before I go to, or 10 minutes of questions before I go to the GitHub, and just get you started on that. if anyone has a question, or I will go straight to the GitHub. I see questions. No, no question. Pakoda is present. He was here, then he went. let me go to the GitHub, and then I think there will be lots of questions next time. So, and meanwhile, if you think of a question, just ask me. Okay. So let me go back to screen share. And once you really start trying it, hopefully you will enjoy it and there will be more questions. So hopefully you can see my Chrome again. Great. If anyone cannot see my Google Chrome shared, then let me know. So I'm on github.com/tiwarilab. If you go down, you will see SPIP PLUMED Masterclass 2022. So this is really many thanks to my graduate student Shams, who created this, and Dedi, who also created this. And we have two tutorials here. The first one involves a model 4-state system. The second one involves alanine dipeptide. So the first one, both of these systems are covered in this paper in state predictive information bottleneck. You should be able to reproduce all of the results of this paper by running this. So let's go to the first tutorial. And the way it is set up is that you can use it in Google Colab and everything will work nicely. So today I'm going to walk you through the first tutorial. The second tutorial, I'm not going to show you anything. That's totally up to you. And at end of both of the tutorials, there are some exercises. This one has 3 exercises that you really should try, and hopefully you will get more involved in the method if you try it. And the other tutorial also has some examples. So so once you go to Google Colab, edit, let's clear all outputs. So this one does not need GPUs. Well, I have hardware accelerated GPU on, but I think you can run it even, and Colab provides it for free anyway, so there's no problem. So the objective of this first tutorial is it will help you understand the theory that I just showed you. You will use this to analyze a 4-state system trajectory. For this one, we have performed longevity dynamics, I think using the Bussy thermostat and Bussy Parinello thermostat, and the trajectory is provided here. It will help you understand some of the SPIP hyperparameters and will really get you ready to perform the next set of bias simulations. So this one, we have prepared everything. So run anyway. It will install Conda on Google Colab for you. And it's not very slow. We will be able to finish it in the next 10 minutes, the full thing. And this one, I really want to walk you through the full answer of the tutorial before the exercise, because it's a much better way of appreciating how everything works. And if you have any question that comes to your mind, just interrupt and ask me. Okay, so that ran. And in this second step, it will ask you to manually type yes at some point. Maybe there is a shortcut to avoid that. I could not quite figure it out. Should be done within a few seconds. Okay, all done. So at this step, if you type, some of you probably know this, in Colab, it is just like shell, but if you're typing any shell command, you have to type an exclamation mark before it. So if you type exclamation mark plumed help, everything came out nicely. You got something that looks like this. So as I mentioned earlier, the basic framework behind state predictive information bottleneck is like this. You have some input trajectory and you're trying to predict something into the future. These are labels, so we are using Y. Now, one thing to keep in mind, and here the nuances come into the picture. When you are using such variational type autoencoder type methods, the latent variable is actually composed of two things. It fits the mean of the latent variable. It also predicts the noise of the latent variable. So it is inherently stochastic. There are some frameworks where this noise is adjusted on the fly. Typically in SPIB and in many autoencoder methods, some constant value is left. And this really makes the method very robust by inherently having noise in the latent variable. But for the purpose of biasing or analyzing, we are going to look at the mean of the latent variable. So SPIB works as follows. We come up with some initial guess of the state labels. As you saw for alanine dipeptide, we came up with the initial guess along phi variable. We perform state predictive information bottleneck. It will refine the state labels. If you are getting the same answer that you started with, that means you are converged. If not, well, better go and repeat and see what's going on. Once this procedure converges, then you stop and you output the converged reaction coordinate and state labels. So this is already very useful for analyzing long unbiased MD trajectories. You are getting the reaction coordinate, you are getting how many states are there, you can repeat the procedure for a different delta t. So it's super useful. You can even do in principle on an experimental trajectory and analyze things. In the other tutorial, you will see then how this is used to bias metadynamics. Okay, so this is the basic framework. We are not going to clone the code from the Git, and then we are going to just get ready for plotting in Python. So there is already a trajectory that has been created for you in the Git that we are going to use over here. And let's visualize this trajectory. So this trajectory, it's a 4-state system along 2 coordinates. And the x coordinate, you can see, shows you the 4 states. The y coordinate is kind of diffuse. It's mostly noise, okay? So this is the trajectory that you have loaded. And you can visualize the underlying, and you can see this is the potential energy form that was used to run this dynamics. And it looks like this, okay? So this is the analytical potential. So you have 4 states along x. There is a dominant barrier in the middle, and there are 2 smaller barriers. And if you take the MD trajectory, it of course looks noisy, and you can see there is a smaller barrier here, and then a very high barrier in the middle. It's a 2-state system, so this is technically a potential energy. So we are going to generate some labels along x. That procedure is shown over here, how to do. So we do that, and we visualize the labels. So what we have done is to generate labels along x that go from 0 to 9. So for many practical systems, so you might say at this point, well, x is already very close to the reaction coordinates, so you lucked out. So in the exercises, I have asked you to generate labels completely along y or along some rotation coordinate, and then repeat the remaining procedure. You can do that by just modifying this code. So it will work for all of that. And indeed, if you don't know anything about any other parameter that could be used to characterize the labels, in this paper, well, in this paper, let's see if I can find it. I just found the archive, but the paper is on JCTC, where we also show a temporal initial labeling scheme, where we just take time lapses of the system and call them as different labels. So first 1 nanosecond is state 1, second nanosecond is state 2, and something like that. And if you have really no clue of where the states might be, I recommend using that. And this paper shows all of that. So let's go down. So at this point, we have generated labels along X and visualize them. We have started with 10 labels. You can add more and see how it looks. Now we are going to run SPIB. It's really simple. We are going to specify a bunch of codes, DT commands. DT is time delay, how far into the future you're trying to predict. Minus D is the dimensionality of the reaction coordinate. So in this case, we are predicting 50 time steps into the future. We are using a 1D latent variable. Our encoder is non-linear. We are going to, and you could just change it to linear, it will work. Minus BF is the batch size. This is something that changes with the length of the trajectory. Next class, my student Shams will also be here. He can tell you some heuristics on this. Threshold is, so if you do one round and the state population did not change, that does not mean you have converged, right? You really see whether the population has truly converged through different rounds, and that is all implemented over here. And then there are some other parameters coming from machine learning, learning rate and some labels and stuff like that. But the most important thing is how much into the future you are predicting, the dimensionality of the reaction coordinate, and the encoder type. These are the most important things. So let's run this. And once we run this, we are going to visualize the results. We are going to look at where are the final number of states after convergence, how many are there and where are they located, and how does the reaction coordinate look in the 2D space. So let me start running it, and then I'll talk a little bit more. So it's running in Colab directly. It will not take a lot of time, maybe 3 or 4 minutes for this system. So any questions about the part so far as this runs? So you can see it's printing out the population of the change in the state's population, and once it converges, it will stop. If you look at it, you can already see. So we started with 10 states, right? So you can see if we go far up, does it print that? So you can see we had population in 1, 2, 3, 4 of the states. So already very quickly it had picked up that 6, because this is after 500 iterations, right? So already after 500 iterations of the training, not 500 iterations of adjusting state number, it had picked up that 6 of the states don't have population, only 4 really have populations. And that's where it's going to converge. And you can make it converge faster if you are less aggressive with the convergence parameters. Okay, so that finished. Now we can plot it. We will, in order to do this, oh, I did something stupid. I did not load this one. So now we have to load the result. Okay. So we have learned the mean. You remember I told you that the latent variable has a mean and a variance. So we have learned the mean, and we have also, these files were created. So, and we have loaded the mean, and we have also loaded the levels. So let's plot the learned state levels. As we can see, we started with 10, but it has converged to tell us that 6 of them don't matter. For this particular DT, we got 4 states. So my question for you is, what would happen if I made DT 100 times larger or 10,000 times larger? Would you expect the number of converged states to become smaller, or less number of converged states, or more number of converged states? Any answer? You can type it in the chat. If I made DT 1,000 times larger, will the number of converged states increase or decrease? Decrease. Why, Giovanni? It's okay. I trust Giovanni.
Yeah.
Eh?
I guess because in a very short time, in that time, I mean, the system will be able to visit all of them.
Yeah, exactly. So the best way to debug the method the first time you're using it in your system is to take an absurdly large DT, and you should get 1 state. And when you make DT equal to 1, you should get lots of states. If that is not happening, you have a bug somewhere in using it. Thanks, Giovanni. Sorry for putting you on the spot. So, and then we can visualize the reaction coordinate. This is a 1D reaction coordinate, so we can directly visualize it. And you can see it's automatically capturing everything going from state 1 to 2 to 3 to 4. So that's what we have over here. So the exercise in this tutorial that I wanted to try is to mention that what I said, you should play with the DT so that the number of converged states that you get is 1. This is already very easy. Just go to very large value. For 2, you will have to stay in some intermediate range. And for 4, you can go to, and you can even try DT is equal to 0 and see what goes on. The next thing I would like you to do is to systematically scan across a range of DT values and make a plot where the y-axis is the number of converged states you get, and x-axis is the corresponding DT value. And these things are in the paper, in the original JCP paper by Wang and Tiwari. So you can compare with it if you want. And this one is a bit harder, but it's really worth doing it, is to assign labels along y. If you assign initial labels along y, you will find the method fails. It won't work. This is similar to alanine dipeptide assigning labels along theta. It's not going to work. But if you assign labels along x is equal to y in this direction, so you're not doing labels along the perfect reaction coordinate, but something rotated from it, or in fact, you can take it to the limit where you're assigning labels along this line, which is maybe 70 or 80 degree from x, you will still get the right result. So this is the first set of tutorials. I already ran it for you. It's very easy, but it's really important that if you're interested in using this method, it's very important that you try this out. Now I want to briefly show you the second set of tutorials, and I want to show you why it's quite nice. Is because what Shams did here is to show this. This is the first one is for understanding. The second one is really which will help you to get the method to work on your problem. It's only alanine dipeptide. The reason it's alanine dipeptide is because you can run it within half an hour on Colab, so you don't need to have your GROMACS installation. Everything is done over here, and we are providing you the .gro, .mdp, .top files. We are also providing an unbiased trajectory to get started with. You can generate it yourself if you wish. And in this one, you will be able to visualize this trajectory. You can see that it's it does not have a lot of transitions between the states of interest. It goes there only once. But from this, you will do initial state assignments along phi. You have 10 states or whatever, and you can change it. You can do 20, and that will work. You can select hyperparameters. You can really nicely play with everything over here, and and then you will run a SPIB over here, and you will get convert states. In this case, for this particular DT, you are going to get 3 states, and you will see how it nicely corresponds to the transition state ensemble. In that projection. And now what I like here is that you can run GROMACS directly in Colab. So you don't have to go run it on a supercomputer. You can directly run it over here, and you can do everything. It will generate a Colvar file that should look something like this. And then you can visualize it. So here we have given you some harder exercises, which is to not use sine and cosine, directly use the dihedral angle to train SPIB and bias and see what happens. It actually will work for this system. And then you should try playing with the number of neurons in the encoder and decoder. And we have also made provided you access to the PLUMED nest files for this paper, where we provide results for AIB9. And if you do unbiased MD, you get no transition between left and right-handed. If you do biased along our coordinate, you get lots and lots of transitions without hysteresis. So the files are available in PLUMED nest for that one. And this is something you can download those. This you won't be able to run in Google Colab. You will have to do it on your computer. But in principle, it should be totally possible for you to reproduce all the results from that paper. So it's a lot of work, but I think if you start using this, there are 2 things. First of all, you can hopefully get use from it for analyzing your molecular dynamics trajectories or for biasing simulations. It's useful for both of them. And secondly, we are always interested in the method improving. If you come up with something that you think can do better than our method, please go and publish it. Nothing will make us happier. And if any questions at this point? Good. So if there are no questions, normally that means I spoke too fast or everything was too clear. Hopefully it's in the second category. Given that at least 2-3 people did get my answer correct about what happens with very large DT, so it's not completely miss. But try the tutorials. There is a Slack channel. I think I will. Some people joined later. So Giovanni, could you post the Slack link once? Or I will just copy paste.
Yeah, I already posted it the second time. And yeah, in case anyone missed it, just ask by email.
So please join the Slack channel, try the tutorials. We would be very interested to see how you like it. Maybe it will help us improve the tutorials. And I think I have to talk to Giovanni and Max on how to maybe clean up the tutorials so it can be used in the Plume documents. And yeah. Okay, I guess. Thank you, Giovanni. Thank you, Max, for the opportunity.
Thanks, Pratyush. And yeah, let me stress with everyone that, yeah, please try to do the exercises and try to ask questions on Slack. So try to exploit the availability of Pratyush in case you have troubles doing the exercises.
The exercises are really very, very easy. We have been giving it to undergraduate students in my group and they get it going without any problem. It's easy, try it. And once you do both these sets of exercises, you are ready to go for your complicated system. It won't be much of a learning curve.
So feel free to ask questions on Slack about your complicated system, I guess.
Yeah, absolutely. That's the hope. Okay, take care, everyone.
Okay.
Bye-bye.
Thanks, everyone. Bye-bye.